The story you were told about Betelgeuse is no longer the story scientists believe. The 100,000-year timeline collapsed 18 months ago, quietly, in a series of journal articles almost nobody outside professional astronomy has read. The 2019 Great Dimming was not a dust cloud. The star itself cooled. There is a hidden companion ripping its envelope apart on a 5.78-year orbit. Mass is bleeding off the surface faster than the textbook ever predicted. And the entire scientific consensus on when this star will detonate has shifted from comfortably distant to, quote, uncertain by orders of magnitude, which is the polite professional way of saying it could happen tomorrow. Stay with me, because today I am going to show you what the warning will look like when it comes. Let's get into it. Imagine you are walking down Fifth Avenue in New York City at sunset. The sun is dropping below the skyline in the west, and the orange glow is doing what an orange glow always does. Normal evening. But something feels wrong. Your shadow is stretching in two directions. You turn east, and there it is, blazing through the twilight like a second sun, a brilliant white star with a blood-red halo. So bright it hurts to look at directly. So bright it is, casting a second shadow of your body across the pavement. The red shadow is sharp and cold, and it is pointing west, away from the rising star. This is not a movie, and it is not a simulation, and the strange thing is that nothing about this scene is implausible anymore. There is a star in our cosmic neighborhood that is actively destabilizing, and the timeline we were promised has shattered, and the only question left is when the light finally arrives. The star is Betelgeuse. You know it. Most people do, even if they do not realize it. It is the bright red point that marks the left shoulder of the constellation Orion the Hunter, the one that looks faintly orange to the naked eye, the one that sits there every winter night like it has been there forever. And for most of recorded history, Betelgeuse was background scenery, a fixed point, a reliable star, the kind of thing you used to navigate by, or to set the dates of religious festivals, or just to look up at and feel small. The official line, the one that came from textbooks and observatories and every astronomy class anyone has ever taken, was that Betelgeuse was stable for another 100,000 years. Watch and wait, they said. No rush. There is no urgency here. The star will go supernova eventually, but eventually means a span of time longer than human civilization has existed. That story, the one we were all sold, has quietly collapsed in the last 18 months. And almost nobody is talking about it. To understand why, you have to go back to the autumn of 2019. This is the moment everything changed, even if nobody quite realized it yet. Between October of 2019 and February of 2020, Betelgeuse did something it had never done in the history of modern observation. It dimmed, not by a little. The star's apparent brightness dropped from its normal range, around magnitude 0.4 to 0.6, all the way down to magnitude 1.6. It lost roughly 60% of its visible light output. To anyone looking up at Orion that winter, the constellation looked wrong. The Hunter's shoulder had gone faint. Astronomers called it the Great Dimming, and for the first few months, nobody had a clean explanation. Two competing theories emerged. The first was the dust hypothesis. The idea was that Betelgeuse had recently coughed up some material from its outer layers, and that material had condensed into a cloud of fine silicate and carbon dust, and that dust was blocking our view of the star. Like fog. The star itself was fine. The dust was just in the way. The second theory was the cool spot hypothesis, which suggested that a large convective downwelling on the southern hemisphere of the star had created a region of significantly cooler photosphere, and that cooler region was simply radiating less light. Two different explanations, two different physical pictures, And for about a year and a half, the scientific community leaned toward the dust hypothesis because it was the simplest fit to the early data. But then the reanalysis started. And this is where the story gets uncomfortable, because the reanalysis is what no one is putting on the front page. When astronomers went back through the high-resolution spectroscopic data, when they pulled the interferometric measurements and ran them through better models, they found something the dust hypothesis could not explain. The surface temperature of Betelgeuse itself had dropped, not by a tiny statistical wobble, but by something on the order of 100 to 200 Kelvin across the integrated photosphere. That is a real cooling event. That is the star itself getting colder. Dust does not cool a star. Dust just stands in front of it. If the temperature itself dropped, then something inside Betelgeuse, something structural, was happening. Something the textbook treatment of the star never accounted for. The current best supported model is a hybrid. A large convective downflow lowered the surface temperature on the southern hemisphere of the star, and the cooler patch then enabled local condensation of dust from material that Betelgeuse's normal stellar wind was already pushing outward. So the dust formation event was real, but it was not the cause. It was the consequence. The cause was a real surface cooling event, and what triggered the cooling event is the part nobody had a good answer to, until they started looking at Betelgeuse in a way they had never looked at it before. That is when they found Siwarha. Stay with me here, because this is the moment the timeline shatters. Astronomers working independently, on different telescopes, in different countries, started finding the same anomaly. A small, hot stellar object hidden in Betelgeuse's glare. Roughly 1 to 1.5 times the mass of our Sun. Hot enough to be picked up in ultraviolet spectroscopy. Massive enough to leave a fingerprint in the radial velocity data. And orbiting Betelgeuse on a period of approximately 5.78 years, which lined up almost perfectly with a long secondary period that had been showing up in Betelgeuse's photometric record for decades. A pulsation that nobody had ever been able to explain. They called the companion star Siwarha. And here is the part that should make your skin go cold. Siwarha's orbit is so tight that at its closest approach, it does not pass beside Betelgeuse. It plunges straight through the supergiant's outer atmosphere. Not through the core, not through the photosphere, but through the chromosphere and the inner regions of the dust-driven wind, like a wrecking ball swinging through fog. Every 5.78 years, this companion star drives directly into Betelgeuse, stirring the plasma, ripping convective cells loose, dragging material out behind it like a wake. And the great dimming of 2020, it happened right after Siwarha's most recent close approach. The companion star plunged through. It tore a piece of the southern hemisphere convective structure free. That structure expanded, cooled, and condensed into a dust cloud that blocked our view, and the temperature drop and the dust formation and the asymmetric southern hemisphere brightness anomaly all clicked into place at once. Not a routine stellar burp. Not a passive evolved star running out a textbook clock. Betelgeuse is being actively perturbed by a star we did not know existed 2 years ago. The question is, what happens next? Because if Siwarha is doing this every time it passes through, then every 5.78 years, Betelgeuse is shedding more mass, losing more of the radiation pressure that holds its envelope up against gravity, and inching closer to the moment its core finally collapses. The next periastron passage is right around now. And if the wake forms again, and if the dust condenses again, and if the next dimming event is worse than the last one, the question stops being how long Betelgeuse has left. The question becomes whether it has already happened. Here is the cruel part of cosmology that nobody warns you about until you have spent enough time staring at it. Betelgeuse is approximately 640 light-years away from Earth. Some of the recent reanalyses of the parallax data push the number out closer to 700 light-years, but 640 is the working anchor. And what that means, if you sit with it for a second, is that every single photon hitting our telescopes today left Betelgeuse roughly 6 centuries ago. The light we are seeing right now, on May 2nd of 2026, departed the star in the year 1386, the Great Dimming. We observed in 2019 and 2020. That actually happened in the late 1370s. The Siwarha periastron we are reconstructing from the most recent data, that occurred sometime around the reign of Richard II of England. Everything we are observing about Betelgeuse, every measurement, every spectrum, every magnitude reading is a 600-year-old recording playing on cosmic delay, which raises a question that astronomers do not love being asked at parties. If the star could have collapsed any time in the last 6 centuries, and we would not yet know, what does it mean to ask whether Betelgeuse is alive? What does present tense even mean at 640 light years? The honest answer is that the present tense, applied to anything that far away, is a polite fiction. We are watching a ghost. The neutron star at the center of the supernova remnant might already exist, sitting there in the constellation Orion, spinning at hundreds of revolutions per second, blasting jets of radiation out into space. We just have not gotten the news yet. The light is still en route, and the most uncomfortable thing about it is that we have absolutely no way to peek ahead. There is no observation we can make that lets us see around the time delay. The information traveling toward us is locked to the speed of light, and the speed of light is the speed limit of the universe. We are stuck waiting. But there is a tiny exception to that rule, a very strange, very physics-heavy exception, and it is going to be the only warning humanity ever gets that the explosion has actually happened. When a massive star like Betelgeuse runs out of nuclear fuel in its core, the process does not end gracefully. The core, which is composed mostly of iron and nickel by that final stage, can no longer generate energy through fusion because iron is the dead end of nuclear physics. Iron does not give up energy when it fuses. It absorbs energy, which means the moment the core hits a critical mass of iron, the radiation pressure that has been holding the star up against its own gravity for millions of years just stops. And the entire stellar core, a mass of material more than the mass of our sun packed into a region the size of a small country, falls inward. It falls fast. It falls in less than a second. And when it slams to a stop against the surface of the newly formed neutron star at the center, it rebounds, it bounces, and it sends a shockwave outward through the rest of the star. That shockwave is what blows the outer layers apart. That is the supernova. But the very first thing to escape the dying star is not the shockwave, and it is not the visible light. It is a flood of neutrinos. Tiny, ghostly particles with almost no mass and almost no interaction with normal matter. Neutrinos pour out of the collapsing core in numbers so enormous that the human mind cannot really hold the figure. The total energy in the neutrino burst from a core collapse supernova is on the order of 100 times more than the energy released as visible light. Most of the energy of the explosion is carried away by these particles, and they leave the core slightly ahead of the shockwave, slightly ahead of the photons, because they barely interact with the dense matter inside the star. They just slip through. This gives us a window, a small, weird, extraordinary window. Because while the photons are still working their way through the outer layers of Betelgeuse, the neutrinos are already on their way to Earth. And when they get here, somewhere between 2 and 48 hours before the visible light catches up, they hit our detectors. Massive tanks of purified water, sitting kilometers underground, in places like Super Kamiokande in Japan. Frozen ice, riddled with sensors, at the Ice Cube Observatory at the South Pole. The SNO Plus detector in a nickel mine in Sudbury, Canada. Camland in Japan. The LVD detector in Italy. These instruments are buried under kilometers of rock and ice for one specific reason: to shield them from every other source of radiation in the universe, so that the only thing left for them to detect is neutrinos. Normally, these detectors register a few neutrino events per day. Background noise from the sun, from cosmic rays, from radioactive decay in the surrounding rock. Trickles. But when Betelgeuse explodes, the same detectors will register tens of thousands of events in roughly 10 seconds. An unmistakable flood. The signal will be so loud, so coincident across multiple detectors on multiple continents, that there will be no question what just happened. And there is a system already in place called the Supernova Early Warning System, or SNOOS, which is designed to do one thing and one thing only. The moment two or more independent neutrino detectors register a coincident burst consistent with a galactic core collapse event, SNOOS automatically issues an alert. The alert is automated. It cannot be suppressed because the data is held jointly by academic consortia in multiple countries. The moment Betelgeuse goes, the world will know within minutes. And then we will have hours, maybe a day, maybe 2 days, depending on how long it takes the shockwave to break out of Betelgeuse's outer layers. A small, brittle window of human anticipation, spanning the gap between knowing the supernova has happened and seeing it happen. Imagine that. Imagine being alive on the morning the alert goes out. Imagine waking up to the news that Betelgeuse has detonated, that somewhere in the constellation Orion, 6 centuries ago, a star died, and that the photons, the actual light from the explosion, are arriving in roughly 24 hours. Schools cancel classes. Observatories open to the public. Every news channel runs continuous coverage. Astronomers explain what to expect, but nobody really knows, because no nearby supernova has exploded since the invention of the telescope, since the invention of photography, since the invention of literally anything we use to study stars. The last unambiguous galactic supernova visible to the naked eye was in the year 1604, observed by Johannes Kepler. That was 422 years ago. Nobody alive has experienced this. Nobody. So the window opens. Hours pass. The eastern horizon tilts toward the constellation Orion. People stand on rooftops, holding phones. Cameras point. Radio chatter fills the air. And then, at some moment that nobody can predict to the minute, the star starts to brighten. That is the part you have to brace for. Because what happens next is a kind of light no one in modern history has seen. Picture this. You are standing outside, somewhere quiet, somewhere where you can see the eastern horizon. Maybe you have stepped out into your backyard. Maybe you are on a rooftop in a city. Maybe you are on a beach, or in a parking lot, or in the middle of a field. The constellation Orion is up. You know where Betelgeuse is. You have been told to watch the left shoulder of the hunter. And then it happens. Not all at once. The brightening is gradual at first. Within an hour, Betelgeuse rivals Venus, which is the brightest planet in the sky and a familiar reference for anyone who has ever looked up. Within a few more hours, it surpasses Venus. It surpasses every other star in the sky. It surpasses Jupiter, which is normally one of the brightest objects in the night sky after the moon. It keeps climbing. And within 12 to 24 hours, depending on how the light curve plays out, Betelgeuse hits its peak. The peak brightness, according to the standard models, will be somewhere between apparent magnitude, -11, and apparent magnitude, -12. To put that in perspective, the half moon shines at roughly magnitude -10, and the full moon at magnitude -12.7. So Betelgeuse at peak will be brighter than a half moon, and approaching the brightness of a full moon. But here's the part that messes with your perception. The moon spreads its light across half a degree of sky. Betelgeuse will be a single point. All of that brightness, all of that magnitude, will be focused into one piercing pinprick on the celestial sphere. And a point source at that magnitude does not just look bright. It looks unreasonable. It looks wrong. It looks like a hole has opened in space, and the light from somewhere else is bleeding through. You will be able to read a book by it. Not a metaphor. Literally. Magnitude -12 is enough light to read text by in the middle of the night with no other light source. Step out into the yard at midnight on a moonless and clear night, and Betelgeuse will be casting hard shadows. Sharp ones. Defined ones. Hold up your hand, and you will see two shadows on the ground. One from whatever streetlight or porch light happens to be nearby, and one from Betelgeuse. The Betelgeuse shadow will have a faint reddish tint because the supernova's photospheric expansion produces a light that is dominated by hydrogen recombination, with a brilliant white core wrapped in red wings. The image in the channel's hook is not theatrical. A red shadow stretching across the pavement at midnight is an actual physical prediction, and it does not stop at night. This is the part that astronauts and astrophysicists keep emphasizing when they talk about a Betelgeuse event. It will be visible during the day, in broad daylight. A magnitude -11 to -12 point source against a sunlit blue sky is not subtle. Walk outside at noon, look toward the eastern part of the sky, where Orion would be if you could see the constellation, and there will be a star hanging in the daytime sky. Smaller than the sun, fainter than the sun, but unmistakable. A point of red and white light, holding still in the blue. Two suns, one yellow, blazing in the south, one reddish, crisp in the east, both visible to the naked eye, both casting their own light onto the world below. Now, there's going to be a wave of panic. Some of it understandable, some of it whipped up by people who have not done their homework. The panic will sound like this. Is the radiation going to kill us? Is the gamma ray burst going to strip the ozone layer? Is the cosmic ray flux going to give everyone cancer? Are the neutrinos dangerous? Fair questions. So, let me say this very clearly. At 640 light years, Betelgeuse is too far away to threaten Earth's biosphere. The high-energy radiation from a supernova spreads out over the inverse square of distance. By the time it reaches us, it has been diluted by an enormous volume of empty space. The atmosphere absorbs the gamma rays. The neutrinos pass through us without interacting, because that is what neutrinos do. They pass through everything. The visible light is intense? Yes, but it is just visible light. We have lived under sunlight for billions of years and survived. A pinpoint of light in the sky, even a very bright one, is not going to harm anyone. This is a spectacle, not a threat. If Betelgeuse were 50 light years away, we would be in serious trouble. At 640, distance is our shield. The atmosphere holds, so you can stop holding your breath about the radiation. What you cannot stop holding your breath about is how long this is going to last, because Type 2 supernovae are not flashbulbs. They do not peak in a day and fade in a week. They have a structure called the plateau phase, in which the expanding hydrogen envelope of the dying star recombines, and that recombination releases energy at a roughly constant rate for somewhere between 80 and 100 days. So Betelgeuse, at maximum brightness, will burn at maximum brightness for approximately 3 months. Every night when the sun sets, the supernova rises. Brilliant, unwavering, permanent in a way nothing in the night sky has ever been permanent in human memory. Your evening routine, by month 2, will involve walking outside and looking east, because how could you not? The world will not stop staring. Social media will be flooded with photographs and time lapses and people standing on rooftops. Artists will paint it. Poets will write about it. Religious groups will interpret it. Doomsday cults will predict the end of the world. Scientists will go on television to explain that the radiation is not going to hurt anyone. and people will only half believe them, because a thing that bright in the sky does not feel like a thing that does not matter, and it will affect culture in ways nobody is prepared for. For our entire evolutionary history, the stars have been fixed. They have been the most reliable thing in our environment. The sun moves, the moon phases, clouds come and go, but the stars are constant. And then, one of them, one of the most familiar ones, the red one in the shoulder of the hunter, just becomes something else entirely. A blazing point of light bright enough to be seen during the day. For 3 months. The psychological impact of that is something we have never measured, because it has never happened during the lifetime of any culture that recorded its reactions in any way we can read. The closest analogs are the supernova of 1006, the brightest in recorded history, observed across multiple civilizations, and the supernova of 1054, which produced the Crab Nebula, and which Chinese and Arab and Native American astronomers documented in fascinating detail. Both events shifted religious cosmology. Both events were interpreted as omens. Both events were absorbed into the cultural memory of every society that watched them. A modern Betelgeuse event, with social media and worldwide instant communication, and a planet of 8 billion people staring at the sky simultaneously, is going to be something else entirely. We will not just watch it. We will photograph it, share it, study it, argue about it, panic about it, and eventually adapt to it. Until, after about 3 months, the light curve starts to drop, slowly at first. Magnitude -12 becomes -10, then -8, then -5. Within 6 months, it slips below 0, below the brightness of the brightest stars in the normal night sky. Within a year, you need binoculars or a telescope to see it. The supernova fades, and what is left behind is a thin, expanding cloud of gas, a remnant, a wound in the interstellar medium that will keep expanding for tens of thousands of years before it finally dissipates. And at the center, if the models are right, a neutron star, a ball of compressed matter the size of Manhattan with the mass of the sun, spinning, possibly emitting pulses of radiation, possibly visible to radio telescopes, possibly invisible depending on geometry. We will not know until we see what is left. There's a strange detail in the optical physics of a Type II supernova that nobody talks about until you have to live through one. The color of the light shifts over time. At the instant of peak brightness, the photosphere of the dying star is still relatively compact and relatively hot, dominated by emission from hydrogen in the act of recombining onto its protons. That gives a light dominated by white and blue tones, with the characteristic red wings from the cooler outer wisps of the expanding shell. As the days pass and the photosphere keeps expanding outward, the surface temperature of that expanding shell drops and the light reddens. By the end of the plateau phase, 90 days in, the supernova will look noticeably more orange than it did on the first night. It will feel like the second sun is slowly setting, even though it is still putting out enormous amounts of light. The reddening is gradual enough that nobody will notice it night to night. But pull up your photographs from the first week and compare them to your photographs from the third month, and you will see 2 different colors of star. The same explosion, just at different stages of cooling. There is something melancholy about that, like watching a fire slowly bank down to embers, except the embers are still bright enough to read by. And while the visible color of the supernova is shifting, every observatory on Earth and in orbit will be pointed at it, recording every wavelength they can capture. Radio telescopes will track the expanding shockwave as it plows into the surrounding interstellar medium and starts emitting synchrotron radiation. X-ray observatories will watch for the eventual breakout of the shock through the outer edge of the star's circumstellar material. Infrared telescopes will track the dust that condenses in the cooling supernova ejecta. Spectroscopists will monitor the chemical fingerprints of every element produced in the explosion, the iron and the cobalt, and the nickel, and the trace amounts of every heavier element that gets forged in the brief, brutal nuclear furnace of a supernova shockwave. We will get spectra of an exploding star at a distance of 640 light-years, with modern instruments, for the first time in human history. The science alone will rewrite half a dozen subfields of astrophysics. Every textbook on stellar nucleosynthesis will need a new chapter. Every model of supernova light curves will get tested against actual data taken from a target so close that we cannot pretend we are looking at a smudge in another galaxy. The supernova will be a once-in-many-generations gift to the people whose entire careers were built on guessing what one of these events looks like up close. There will also be a lot of people who do not care about any of that, and who will simply stand in their driveways for 3 months looking up. That is going to be most of the planet, honestly, because the truth is that the spectacle is going to be more compelling than the science. For most viewers, the science will be reported on, written about, tweeted about, but the experience of having a second sun in the sky will be the thing nobody can quite escape. It will become the unspoken backdrop of every conversation. People will notice it walking to work. People will notice it driving home. The light will affect the way the world looks at all hours, even when the supernova itself is below the horizon, because cities and mountains and clouds will all glow faintly with reflected light from a source that does not stop being there. The whole psychological texture of life on Earth will shift in subtle ways for a season. And then, slowly, as the supernova fades, the world will go back to looking like the world we know. Almost. The constellation will not be the same. The shoulder of the hunter will not be the same. And the people who lived through it will be a generation that watched a star die in real time. The story will be passed down. The way our great-great-grandparents passed down stories about haunted nights in cities they no longer live in. And Orion will be broken forever. Right now, when you look up at the constellation, you see the belt, 3 stars in a line, and above the belt, 2 bright stars, marking the hunter's shoulders. Betelgeuse on the left, Bellatrix on the right. After the supernova, after the fading, after the year is over, the left shoulder will be empty. Just a faint patch of nebulosity where a star used to be. Children growing up after the explosion will learn about Betelgeuse the way we learn about stars that died long before we were born. They will see photographs of what Orion used to look like. They will read the story in a textbook, but they will never see it because it will be gone. Let's slow down for a second, because there is a question lurking under everything we have just said, and it is the question that should be keeping the planetary defense community awake at night. If the textbook treatment of Betelgeuse was wrong, if the 100,000-year timeline was just an artifact of treating the star as an isolated object when it actually has a hidden companion ripping its envelope apart, then how many other nearby supergiants are running on the same flawed assumption? How many other massive evolved stars in our cosmic neighborhood are quietly being torn apart by gravitational interactions we have not detected yet? The candidates are not obscure. Antares is the bright red star at the center of the constellation Scorpius, roughly 550 light-years from Earth. It is a red supergiant, similar in many ways to Betelgeuse, possibly with a slightly higher mass. Rigel is the bright blue-white star in the foot of Orion, sitting on the opposite side of the constellation from Betelgeuse, at roughly 860 light-years. Deneb is the bright star in the tail of the Swan, the constellation Cygnus, at approximately 2,600 light-years. Then there are the red hypergiants, which are even bigger and even more evolved than ordinary red supergiants. And the candidates there include VY Canis Majoris, which is roughly 3,800 light-years away in the constellation Canis Major, and NML Cygni, which is roughly 5,300 light-years away. All of these stars are massive. All of them are evolved. All of them are candidates to go supernova in the geologically near future. And as far as we know, none of them have a confirmed plunging companion star. But here is the catch. As far as we know does not mean as far as we have looked. It means as far as we have looked using the techniques and assumptions that just got Betelgeuse so wrong. The hidden companion that drives Betelgeuse, Sawarha, was sitting in the data the whole time. We just had not figured out how to see it. Which means Antares could have one, Rigel could have one, Deneb could have one, VY Canis Majoris could have one. Any of them. All of them. The plunging companion class might not be a curiosity. It might be the dominant mechanism by which a certain population of massive stars approaches their final detonation. And if that is true, then the whole field of pre-supernova astronomy has been operating with a systematic blind spot, looking at isolated star evolution models when the actual physical situation involved binary partners that were too faint or too close to detect. The honest version of the next sentence is that we do not yet know which of the candidate stars has a hidden destabilizer and which does not. The dishonest version is the one the public has been told for decades, which is that we have a stable list of supernova candidates, and they are running their textbook clocks. Here is the part that gets weirder. If the plunging companion mechanism is real, and if it accelerates the late-stage fusion sequence, then the order in which nearby supergiants explode might not match the textbook order at all. Betelgeuse is currently at the top of the candidate list because it is bright, nearby, and obviously evolved. But if Antares has a Sawarha of its own, and we just have not detected it yet, then maybe Antares is the next one, or Deneb, or VY Canis Majoris. The candidate ranking we all grew up with is a model. It is not a measurement, and the model just got humiliated by Betelgeuse. There is no reason to assume the model is right about anyone else either. This is where we have to talk about a class of phenomena that astronomers call supernova impostors. Sometimes a massive evolved star, instead of going supernova in the classical sense, undergoes a non-terminal outburst event. A massive ejection of material, a brilliant brightening that can rival a real supernova for months, but which does not actually destroy the progenitor. The most famous example is Eta Carinae. In the early 1840s, Eta Carinae underwent what astronomers call its Great Eruption. The star brightened to roughly magnitude -1, becoming the second brightest star in the entire sky, sustained that brightness for years, and then faded back into relative obscurity. The star itself survived. But the ejected material formed the structure we now call the homunculus nebula, two enormous lobes of gas and dust expanding outward from the original explosion, still visible in modern telescope imagery. Eta Carinae did not die. It just had a tantrum. The reason this matters for Betelgeuse is that nobody can rule out a similar non-terminal outburst. If Sawarha's perturbations strip enough mass from Betelgeuse's envelope without quite triggering the iron core collapse, the result might not be a supernova. It might be an Eta Carinae class event, a brilliant, sustained, civilization-defining brightening that lasts for months or years, and then fades, and leaves the star behind, alive, dimmer, but still there, which would be its own kind of historical event. A second sun in the sky for a year, not 3 months. A dramatic, traumatic, world-altering, brightening event that does not actually end Betelgeuse's life. The textbooks would have to be rewritten. Every documentary about red supergiants would have to be reshot. And we would still be sitting there, looking at a wounded star in Orion, waiting for the actual core collapse to come some unknown number of years later. You see how this branches. You see how the certainty we were sold falls apart. The textbook said Betelgeuse was stable for 100,000 years. The textbook was wrong. The corrected version says Betelgeuse is unstable. The timeline is uncertain by orders of magnitude. The immediate next event might be another dimming, or another mass ejection, or a non-terminal outburst that mimics a supernova, or the actual supernova itself, or nothing visible at all for another few decades. And we cannot tell which one is coming. The light is in transit. The information is locked behind 640 years of cosmic delay. We are sitting on the receiving end of a recording, watching a star do whatever it is doing in slow motion, and the only certainty we have is that the textbook story we were taught in school is no longer the operating consensus among the people who actually study these objects. What is happening to Betelgeuse might be happening to other stars too. We just have not noticed yet. And the moment we do notice, the moment another nearby supergiant gets caught with its own hidden plunging companion, the whole map of the cosmic neighborhood shifts. The next supernova might not be the one we are watching. It might be the one we are not watching. And we will only find out when the neutrino detectors light up. So let's talk about the things you are going to hear in the comments. Because if you have been on the internet for any length of time, you know what is coming. There is a particular flavor of Betelgeuse conspiracy theory that has been circulating online for years, and the destabilization story is going to pour gasoline on it. Let me walk you through the main versions, because each of them deserves a serious response, and because the actual story is, in a strange way, more unsettling than the conspiracies are. The first version goes like this. They are hiding the timeline. The official 100,000-year line was always a deliberate cover. Astronomers have known for years that Betelgeuse was much closer to the edge than the public was told, and the dust cloud explanation in 2020 was promoted because it was reassuring, and the real situation has been classified since the Great Dimming. There is a slightly more sophisticated version of this argument that points to the fact that the official narrative did, in fact, shift, and asks why the shift happened so quietly. Why was there no press conference? Why was the hybrid model rolled out in journal articles instead of broadcast on the evening news? The answer, the boring, honest answer, is that there is no agency that has the institutional power to suppress observational data on Betelgeuse, because the data is collected by hundreds of independent teams using dozens of telescopes around the world. The Very Large Telescope in Chile, the Hubble Space Telescope, the James Webb Space Telescope, ALMA, plus dozens of national observatories, plus a global community of amateur astronomers who track Betelgeuse's brightness night to night and post the data on public databases for anyone to inspect. There is no plausible coordination mechanism that could keep all of those people quiet. What did happen, demonstrably, was that the simplest explanation, dust, fit the early data and got reported. The more complicated explanation, hybrid surface cooling plus dust, emerged only after the spectroscopic and interferometric reanalysis. The narrative shift is real. The cover-up is not. The reason it happened quietly is that science usually happens quietly. Most paradigm shifts in astrophysics are not announced with fireworks. They appear in journal articles, get cited, get incorporated into the next round of papers, and slowly diffuse into the public consciousness over years. The second conspiracy is more dramatic. Betelgeuse has already exploded. The neutrino burst either already arrived and was suppressed, or is about to arrive any moment, and governments are pre-positioning for an announcement. The argument goes that the slow drip of stories about Betelgeuse instability is preparing the public for the inevitable, that the recent news cycle is laying groundwork. Now, I do not love debunking this one too aggressively, because you have to admit at some level that the actual situation is a little uncomfortable. Betelgeuse could have already exploded. We genuinely cannot know until the photons get here, and the neutrinos genuinely will arrive ahead of the visible light. So the conspiracy is making contact with a real piece of the physics. It just gets the institutional part wrong. The Supernova Early Warning System is a network of detectors operated by academic consortia in multiple countries. The trigger for an alert is automated. The data is jointly held. There is no mechanism to suppress a snooze coincident detection, because if the Super Kamiokande team in Japan and the Ice Cube team at the South Pole and the SNO Plus team in Canada all see the same neutrino burst at the same moment, the world finds out within minutes, before any government agency could even draft a press release. The fact that no snooze alert has been issued is, in the most concrete sense possible, evidence that the core has not yet collapsed in the light cone of Earth. However, and this is the part that is true and unsettling, the core could have collapsed yesterday, last week, or last year. The neutrinos could be arriving tomorrow morning. We are not in control of the timeline. We are just receivers. The third conspiracy is the Siwarha conspiracy. The companion star is not what they say it is. It is something more exotic. A primordial black hole, a stripped neutron star, an artificial object. The argument is usually framed as a kind of pattern matching. You have an unexplained companion, you have unusual stellar behavior, you have a star that is breaking textbook predictions. Why not consider that the companion is something other than an ordinary main sequence star? The grounded response is that the available data, the radial velocity, the photometric, the ultraviolet spectroscopic, all fit an ordinary low-mass main sequence companion of A-type or early F-type spectral classification. Occam's razor strongly prefers the boring answer. The companion has not been directly imaged, because Betelgeuse is so much brighter than its companion that direct imaging is technically very hard, and the companion is inferred from its effects rather than seen directly. So the absolute determination of its physical nature awaits direct imaging campaigns from the next generation of telescopes. We do not yet have a photograph of Siwarha. We have its fingerprint, and the fingerprint is consistent with an ordinary star. The fourth thing the audience is going to ask, and this one is more interesting, is whether all of this is connected to the other anomalies the channel has been tracking. Whether the destabilization of Betelgeuse, the deuterium signature in 3I Atlas, the global fireball surge, the unusual interstellar object population are all symptoms of something larger, some kind of cosmic phase change, some kind of universe entering an active period. The honest answer is that there is no demonstrated physical mechanism that would connect a stellar instability in a star 640 light-years away to a small interstellar object passing through our solar system or to a fireball surge over the United States. These are independent phenomena observed in roughly the same calendar window. Light from Betelgeuse arrives at Earth from a fixed direction with a fixed time delay. 3I Atlas was a small body on a hyperbolic orbit through the inner solar system. The fireball surge has its own internal explanation, the rock comet stream identified by Hayden Schober's 2026 paper. The geometries do not match. The timescales do not match. The mechanisms do not match. They are separate stories. But, and this is a real but, the closing observation has some weight. We are observing the universe with instruments and at scales we have never used before. The James Webb Space Telescope has been operating for less than 4 years. The all-sky fireball networks are recording at sensitivities. The previous generation of meteor detectors could not match. The neutrino detectors at IceCube and Super Kamiokande are picking up signals that earlier instruments would have missed entirely. So a portion of what looks like an active universe to us is genuinely an active universe, and a portion of it is just better instrumentation revealing activity that was always there. The question of which fraction is open, and the question of whether we are missing some larger pattern that ties some of these events together, even if no one has identified the mechanism, is also open. Pattern recognition is the channel's territory, and the audience knows it. I am not going to tell you the answer is simple. I am going to tell you that the most defensible position is something close to humility. We are a young species watching the cosmos for a few centuries. We have been doing it carefully for a few decades. The fact that we are noticing more strange things now than we did 100 years ago is partly because more strange things are happening, and partly because we have better tools to see them. Both can be true at once, and both should keep you watching the sky. So where does this leave us? You have a star 640 light years away, in the shoulder of a constellation visible from almost every populated part of Earth in the winter months. That star is being actively destabilized by a hidden companion that we did not know existed 3 years ago. The companion plunges through the star's outer atmosphere every 5.78 years, ripping convective material loose, accelerating the mass loss, accelerating the core compression, accelerating the clock. The textbook timeline has collapsed. The remaining lifetime estimate, 100,000 years, is no longer the consensus. It might be 10,000 years. It might be 1,000 years. It might be 100 years. It might be 30 years. It might be 3. The uncertainty is real, and the uncertainty is now formally acknowledged in the professional literature, even if it has not yet diffused into the public consciousness. The neutrino detectors are running. They are running tonight. Super Kamiokande in the Mozumi mine in Japan, Ice Cube at the South Pole, SNO Plus in the Sudbury mine in Canada, Camland, LVD, Boksun. They are watching, and they are coordinating, and the moment the signal arrives, the alert will go out automatically, and the world will have somewhere between 2 hours and 2 days of warning before the photons follow. That is the warning we will get. That is the only warning that matters. And in that warning window, we will all become a single audience. 8 billion people. Looking east. Waiting. Not since the year 1604, when Johannes Kepler watched his star bloom in the constellation Ophiuchus, has humanity stood in collective anticipation of a sky event of this scale. And we will do it with smartphones in our hands, and live streaming cameras pointed at the horizon, and conspiracy theorists shouting on every platform, and astronomers giving interviews on every channel, and religious leaders interpreting it through their own frameworks. And every one of those reactions will be valid, because nobody, and I mean nobody, has been here before. There is something almost poetic about the fact that the warning will come from the dark. From physics most people have never heard of, deposited into instruments buried under kilometers of rock and ice. Instruments built to detect the only particles that pass through the entire Earth without noticing. Neutrinos are the most antisocial particles in the universe. They barely interact. They barely exist by some philosophical definitions of existence. And yet, when Betelgeuse finally goes, it will be these ghost particles, not the photons that paint our skies, that tell us first. The visible light comes second. The neutrinos come first. And that is the small, weird, beautiful asymmetry that gives us our window. If you take one thing away from this, take this. The sky is not as fixed as you have been told. The textbooks compress unimaginable spans of time into present tense statements, and they do this for the convenience of our species, because we are short-lived and we need a stable picture of the cosmos to organize our lives around. But the cosmos itself is not stable. It is just slow. Stars die. Stars destabilize. Stars get torn apart by binary companions we cannot see. And every one of those events ripples outward at the speed of light and arrives at our telescopes 6 centuries late, like a letter from the past. We are the recipients of a constant stream of stellar correspondence, and the correspondence we are reading right now contains, in its margins, a warning. A warning that the star in the shoulder of Orion is not what it used to be. A warning that the timeline has shifted. A warning that we should keep watching. Here's the thing about Betelgeuse that I cannot stop thinking about. The light we are seeing tonight, on May 2nd of 2026, left that star in the year 1386. In the year 1386, the Black Death had ravaged Europe a generation earlier. Geoffrey Chaucer was writing the Canterbury Tales. The Ming Dynasty was 20 years old. Tamerlane was conquering Central Asia. Nobody on Earth knew that Betelgeuse existed in the way we know it now, Nobody had a telescope. Nobody had spectroscopy. Nobody had any concept of stellar nucleosynthesis, or core collapse, or supernovae. The light we are seeing tonight was emitted by a star that had been doing what it was doing for millions of years before any human being ever looked up and gave it a name. And in the 600 years since that light departed, the star may have continued to evolve, may have continued to lose mass, may have undergone events we have not yet seen, may have died and become a neutron star, may be sitting in the constellation Orion right now as a faint expanding remnant whose news has not yet reached us. We are reading old mail. The new mail is in transit, and the new mail might be the brightest piece of mail any human civilization has ever received. When it arrives, when the neutrino alert finally goes out, when the eastern horizon brightens and the second sun rises, you will know what to do. You will go outside. You will look up. You will see the star you have been watching all your life become something else. A dying star. 600 years, too late to help, but close enough to feel. The world will stop briefly. The world will stare. And then, after 3 months at peak brightness, the star will begin its slow fade, and over the course of the year that follows, the constellation of Orion will be permanently altered. The hunter will lose his shoulder. Children born after the supernova will grow up looking at a different sky than the one we grew up under. They will learn about Betelgeuse in history class. They will see photographs of Orion the way it used to look. And they will believe us, in the abstract way you believe anything you read about a vanished world, because by then, Betelgeuse will be a story rather than a star. I cannot tell you when this will happen. Nobody can. The honest professional answer to the question of when Betelgeuse will go supernova is some unknown number of years, with a probability distribution that runs from days to millennia, and a cluster of physical reasons to think the median has dropped from where it was a decade ago. Maybe you live to see it. Maybe your children do. Maybe none of us alive today will see it, and the light will arrive at the telescope of some future astronomer who will recognize immediately what they are looking at, and who will inherit the warning the rest of us spent our lives waiting for. So here's the real question, the one the channel keeps coming back to. Are we entering a new era, a phase of the universe in which stellar deaths are coming more frequently, or in which the patterns of cosmic events are shifting in ways we are only beginning to detect? Or have we just been blind until now, and what we are seeing is the actual baseline rate that has always been there, finally visible because of better instruments and faster information sharing? I do not know the answer. Nobody does. What I do know is that the next time you step outside on a winter night and look up at the constellation Orion, the red point in the hunter's shoulder is not the boring background star you grew up with. It is a wounded thing. A star with a hidden companion ripping its envelope open. A star whose death may have already happened, with the news still in transit. A star that, on some night, in some year, near or far, will brighten in the east until you can read by it, and the world will stop everything to watch. Subscribe if you have not already, because the moment those neutrino detectors light up, you will find out here first. Drop a comment letting me know where you are watching from, and what you would do in the 24 hours between the alert and the arrival of the light. Would you stay home? Drive somewhere dark? Climb a roof? Call your family? Stand in your backyard and just look up? I have my answer. I want to hear yours. Betelgeuse is counting down, and so are we.